So you've learned how carbon dioxide has gotten into our atmosphere and how humans have kind of been increasing it over time. Now, while we understand kind of the basic chemistry that explains that, what we don't have yet, or the piece of the puzzle I haven't really talked about yet, is it like a lot? Like when we're saying, oh yes, humans are doing this, okay, but how much does that matter? Like, are we adding a whole bunch? Are we adding, sure, we're adding some, but it doesn't make a big impact, etc. So that's what we're going to explore in this video. It's kind of the data that we have showing how carbon dioxide has been changing in our atmosphere. And so what we're going to first take a look at is kind of this iconic, they call it the hockey stick graph, because it kind of looks like a hockey stick, right? Here's the handle and here's the part that's on the ice, whatever it's called. Anyway, what we're looking at is carbon dioxide from the past 800,000 years. And that kind of sounds crazy, and we're going to talk about that. Let me actually get a pen out. So let me put this in context for you. Humans, as in Homo sapiens, didn't really start evolving until about 200,000 years ago. And I mention that because there is no way that we have been measuring carbon dioxide all of this time. This data comes from ice cores, specifically from Antarctica. Not that that really matters, but so ice cores, it kind of works like soil. Growing up, you probably learned about dinosaurs and how dinosaurs found in lower layers of rock were older than higher layers because of compaction and stuff like that. Ice is the same exact way, right? It snows, and if it never melts, like it just snows on top of that snow and snows on top of that snow, and it compresses, which melts it into ice. So ice and snow work the same way. So in Antarctica, what we've actually been able to do is we take cores. So it's like literally this cylinder of ice, and we drill down, and we drill down pretty freaking deep. And just like soil, scientists are able to estimate what year that ice formed. Now, if you have ever looked at an ice cube, and if you look it through your ice cube, you might notice there's air bubbles in it. That just happens when water's freezing. Well, scientists literally take this like super fine needle and essentially stab air bubbles that are in this ice core from, again, different years ago, and they can suck the air out of it. And that air is essentially a pocket of air from 500,000, 600,000, 700,000 years ago. And they're able to run a composition analysis where they can tell, oh, in this sample, there's this amount of oxygen, there's this amount of nitrogen, there's this amount of carbon dioxide. So that's where like all this data pre-early 1900s comes from. It comes from these ice cores, and it's not just one ice core. Like this has been done over and over and over again to kind of ensure that like their methodology is sound. So here's what you can see. I'm going to ignore present day. So x-axis is years. We've kind of explained how we got so far back. Y-axis is carbon dioxide concentration, and there's this unit, ppm. ppm stands for parts per million. And that kind of is what it sounds like. If I have 1,000,000 molecules, then 200 of those molecules is carbon dioxide. 300 molecules are carbon dioxide. So when we say it's ppm, it's how many molecules of whatever, in this case carbon dioxide, per 1 million particles it's mixed in. We think of carbon dioxide, it's mixed in air, right? It's mixed in nitrogen and oxygen and stuff like that. Now, that doesn't sound like a lot. And like, I guess in the grand scheme of things, right, 200 out of 1,000,000 isn't a lot. But if you watch an earlier video about the greenhouse effect, we don't need a lot, is the thing, right? We don't need a lot of carbon dioxide to get adequate levels of warming to keep us warm enough here on Earth. So go watch that video if you need some more background on that. Okay, so let's look at, again, the distant past. So you can see carbon dioxide naturally fluctuates in our atmosphere. And for simplicity's sake, it fluctuates between 200 and 300 parts per million. It goes under 200, but again, let's keep it simple. To give you an idea of kind of the relationship between carbon dioxide and temperature, I've added this line in here. Every time carbon dioxide is below this black line that says ice ages, Earth is in an ice age. So here, that's the last ice age. This is the saber-toothed tiger, mammoths ice age. That's from like 10,000 years ago. Earth has been through many more ice ages. We just don't have videos about them. We don't have Pixar movies related to them. So when people say, oh, the ice age, they're referring to the most recent one, but we've had a ton in Earth's history. Okay. Let's talk about how long it takes for things to change, because that's kind of important too. So I'm going to look for the most drastic change. It's probably this one right here. So our low, oh God, I realize this is a crooked line. I feel like I got back on track though. This looks to be about 400, and that's 50, let's say 30. Oh God. That says 430, whether you believe me or not. So about 430,000 years ago. And then it increased and increased and increased. And I would say that the maximum is probably what, right here? Okay, and that's, 400. Okay. So if we take the difference in time, if my question is how long does it take to go from the low point to the high point? How long does that take? It would take about 30,000 years. That's how wide this is. And again, that's going to fluctuate, right? If you're like, well, you should have done it from like the peak, or not even the peak, but when it first started leveling off. Well, if I did that, that'd be about, oh God, about there. That probably would have been like 10,000 years. My point is, we're talking about tens of thousands of years for carbon dioxide to fluctuate, like between these cycles. And the actual cycle is actually a lot longer. But that 30,000 years is like how long it took to go from the bottom to the top. And again, you could play with that a little bit, but either way, it's going to be thousands of years. And I mention that because if you look here, right, here's like, this has 2008. Here's where humans are. Now this is 2008. I actually have some more recent data. So as February 2024, this is the most recent data I had to me when I made this video, we were sitting at about 424 parts per million. So we're higher than this 2008 line. Look at how much we have gone above 300, right? We're above 400 now. And this is where we start worrying. We start worrying because if we look at our most recent history of 800,000 years, Earth hasn't been this high. Now, I will fairly say Earth has been this high in general in the more distant past. Like dinosaur age type things when humans weren't around. So Earth has been warmer, but again, we want to use more recent history because the more recent history is a better characterization of what Earth is like now. And we just haven't been this hot with the current conditions on Earth. Or we haven't had this much carbon dioxide, which incidentally also means more heat because it's a greenhouse gas. Also, sure, we were coming in, like you may have noticed from that last ice age, we are in like our peak carbon dioxide as it is. But peak carbon dioxide is like 300 parts per million. And we're over that, right? We're at 400 parts per million. So this is where our concern is. Our other concern comes from the data we've been actively collecting. So that previous graph, nearly all of that data was from ice cores. But in the late 1950s, we, as in human society, we have started directly measuring global carbon dioxide to get a more accurate picture of what's happening in our atmosphere. We've been measuring this. We've been measuring in a lot of different areas, but kind of the gold standard is at Mauna Loa. So that's this right here, Mauna Loa. Mauna Loa is in Hawaii. And while that sounds like a really nice job, and I'm sure it pretty much is, it's actually there scientifically for a reason. If you're not familiar with the geography of Hawaii or where Hawaii is in the world, it's like in the middle of the Pacific Ocean. This is good because if we were measuring carbon dioxide, say in downtown New York City, where there's a lot of vehicles, a lot of electricity production, a lot of CO2 emissions, our values would be artificially high. By measuring literally in the middle of nowhere, you have pretty much as unbiased a sample as you can get. Now, Hawaiians use cars and stuff like that, but again, their population's low. They're not getting their atmosphere is not getting influence from other regions because they're in the middle of the ocean. So it's actually a really good place to be measuring. So let's take a look at this. You'll see there's two lines. We're going to talk more about that on the next slide, but in general, the red line is like the direct measurement. This is what the carbon dioxide was. The black line is kind of like the average. Like if I were to take a few months, because you notice there's this jagged pattern. The point is, they're both showing the same thing, so it doesn't really matter. So here's the year on the x-axis. This is all the data that we have. And then on the y-axis it says CO2, carbon dioxide, mole fraction. For the purpose of the video, this doesn't matter, but what we care about is this ppm, parts per million. It is the same thing. Same y-axis as we saw on the previous slide as well. Also, this data comes from NOAA, as well as some other partners. I mentioned this because NOAA is a U.S. federal government agency. I mentioned that because the U.S. isn't really known for being a leader in climate change mitigation, yet we're the ones who collect all the data on it, and all the data support that climate change is happening. So I say that, it's not like, oh, this is Sweden who's saying it's happening. Well, we're like, well, of course Sweden would say that. They're great. This is the United States, who has not been really awesome being a leader in it, saying it's happening, even if we don't come out and fully say it. And it depends on who's president, blah, blah, blah. But my point is, that should be a good piece of evidence that this is good data. Okay. So what I want to point out, we started measuring this in the 1950s, and you notice, again, rounding for simplicity's sake, that when we first started measuring it, it was about 320. And this is not that much higher than what our maximum had been in the past. Remember, in the past, it fluctuated between 200 and 300 parts per million. Cool. In the late 1950s, we're at 320. We're just barely over the typical pattern. So really not too worried about it. And you look at present day, right? We said earlier it's 424. Again, I'm making this simple. I'm just going to say 420. So between when we first started measuring it in 1958 to today in 2024, we've gone up 100 parts per million. Remember earlier, going from 200 to 300 took between 10 to 30,000 years? I'm going to do shitty math right now. From 2024 to 1958 is like 60-ish years, probably closer to 60 to 70 years. It took us recently to go up 100 parts per million. 60 to 70 years compared to 10 to 30,000. This should be concerning. This is what we're scared of. It's not so much that we're getting higher, which that is a concern. It's also how quickly we're going up. Organisms adapt. Organisms evolve. In the past, they had 10 to 30,000 years to do that. Today, you got 60 to 70, right? And it's only increasing. So this is honestly where the concern is. It's not just how high it's getting, it's how quickly it's getting. And we have data to support how quickly that's happening. All right, one more graph. It is actually the same data from the same observatory, same time period. Well, it is recent, but this is looking at just the most recent 5 years, just to kind of understand the data in general. Again, the black line is kind of this averaged, smoothed out data. Not that it's not important, but I'm not going to focus on it. I'm going to focus on this red line. Something you might notice is it's fluctuating every year. It peaks and it goes down, and it peaks and goes down. despite it going up and down, there's still a general trend of it increasing. So let's talk about that, because it's actually super interesting, even though in general it doesn't make a huge impact, because again, it's still just increasing, but I think it's kind of cool. So if we trace kind of what's happening. All right, so here's 2021, 2022. So this is probably middle of this would probably be like, I don't know, July. Sure. We'll say this is July. This is probably March. And this decline is probably October. And these are all estimates. If you're looking at it and you're like, I think it's September, fine. It doesn't matter. It's not going to change anything. So this yearly cycle where it goes up and it goes down and it continues the same exact way every year is due to plants. And it feels so weird saying that, but it's plants. Plants control everything. But in reality, though, it's not just plants. I mean, it is plants, but it's specifically photosynthesis. Or do you remember photosynthesis? I'll do a quick recap. Photosynthesis is where plants and other photosynthesizing organisms take in carbon dioxide. They also take in water. And they also need the sun, or really just a light source. They take in these things to create glucose, which is C6H12O6. So they create a sugar and they create oxygen. Well, what we're really interested in, because remember, this is a graph documenting carbon dioxide, we're interested in that part of photosynthesis. So these photosynthesizing organisms take carbon dioxide out of the atmosphere, right? And they're turning them into sugars, which really is just making the plant larger, right? That's its growth, more or less, and creating oxygen. So when plants are photosynthesizing is when they're pulling it in. Okay, so we kind of understand why it's happening, but how does that explain the time of year? So this graph is showing that within a yearly cycle, carbon dioxide gets highest in March. March is when trees and plants start emerging again. Beforehand, they died, right? So actually, it might be easier to look at October, right? October is when the trees start losing their leaves. That's when plants start dying. Essentially, photosynthesis doesn't halt, but it severely slows. I mean, if you're a tree, like, you don't have leaves, you can't photosynthesize, right? If you're a plant and you are dead, you cannot photosynthesize. So in October, photosynthesis drastically slows. And because photosynthesis is slowing, carbon dioxide in our atmosphere increases. Because, again, there's no plants to take it out. So it increases and increases and increases until March. March is when leaves start coming out, plants start emerging, and so photosynthesis starts happening, or at least happening a whole lot more. So in March, when everything's coming out, the amount of carbon dioxide in our atmosphere declines, and it's going down a lot until these start dying again and trees and blah, blah, blah. So that kind of explains the cyclical nature. What's interesting is that plants, while they do make an impact on our environment, I mean, whatever they take out just goes right back up. Like, those leaves decomposing, those plants decomposing, that carbon just re-enters the atmosphere. So while trees are important to, mitigating climate change, it's a cycle. Like, yes, they take it out and they do store some, but they also release it too. So it's not like this grand plan to stop climate change, is reforest the world. Like, that's not going to make as big of an impact as people tout it to be. Anyway, so one last component to this. So Hawaii is like near the equator. It's in the northern hemisphere, but it's near the equator. In the southern hemisphere, their spring and fall and photosynthesizers is at different times of year. So you would expect we wouldn't see this cyclical nature when the United States in the northern hemisphere is going through spring and all the plants are emerging and photosynthesizing. In South America, They're going into their fall where everything's dying and no longer taking out carbon dioxide. So you'd think it even up. But that's not actually the case. So here's our globe, here's the equator, here's North America, here's Europe, the northern part of Africa, southern Africa, here's South America. Hey, I think that's actually a pretty good job. Most of the land mass on Earth is in the northern hemisphere. Because most of the land mass on Earth is in the northern hemisphere, that means most of our land plants are in the northern hemisphere. So this trend, this March to October, high to low every year, is due to the northern hemisphere's seasons, essentially. The southern hemisphere, just in comparison, barely has vegetation compared to the northern hemisphere. So the southern hemisphere really isn't influencing this cycle as much as the northern hemisphere is. In the long scheme of things, none of this might matter, but it's cool. It's interesting. This is why we have these peaks every year, is just because the northern hemisphere's got a lot of plants. Simple explanation for it. Okay, so we understand the chemistry as to why carbon dioxide would be increasing. Humans burn carbon-based fuels. Therefore, carbon dioxide is released. And now you've seen the data that support it's not just a little bit. We're releasing a lot compared to how it was before industrialization, really. We have been collecting this data for 70 years now, and it's only increasing even more, even faster. And that's really where our concern is. So we're going to explore in future videos kind of the impacts of this increased carbon dioxide in our atmosphere.